Hello, everybody. Good afternoon, dear colleagues. Can you hear me? I suppose yes. I would like to thank you for your kind attendance, and I hope our webinar to be informative and useful with respect to your needs and interests. This workshop aims to inform the communities of scientists and decision makers acting in the field of health and epidemics. It is the third workshop. It is in a series of workshops that have been provided to European stakeholders and Greek stakeholders, and today it is a workshop that we do for the other side of the... Hello, can you hear me?
There is a comment at the chat saying that I'm on the web, but I cannot hear anything right now. 5 minutes ago, I did.
Okay, look, you don't hear us. Hello, someone of the Greek colleagues, can you hear me?
Yes, I can.
Just hear. Okay. So it seems that there is a problem with one participant that cannot hear us. But
Rejoin.
Maybe if you could kind of rejoin the webinar, maybe it's a kind of problem with your connection.
He can hear us now.
Okay, thank you very much. Thank you. Okay, thank you. So I continue. This webinar today demonstrates through selected use cases the value of the science innovation that has been developed at European Union level in the domains of Earth observation and artificial intelligence for the development of a robust solution to combat mosquito-borne diseases. And specifically, all our action so far is on the West Nile virus outbreak. The webinar comprises of 4 presentations. It highlights validated actions for short to mid-term forecasting of human cases and mosquito populations at various geographic scales in Europe. The first presentation is given by me. It concerns an overview of the whole activity and the concept behind this action. In the following, my colleagues from the National Observatory of Athens and our partners from the company Ecodev SA and the University of Patras in Greece will highlight the modeling and operational aspects of the developed solution as in the agenda you see here in this slide. Finally, yet importantly, I would kindly ask you to keep your questions for the Q&A session of the workshop, which will take place after the presentations. Also, during the presentations, you can use the Q&A facility of this platform, the Zoom platform, so as to submit your question. My colleague here will collect a question and we will reply them, by the end of the webinar, by the end of the presentation, in the same order as we are going to receive the questions. Let's also inform you that this webinar is recorded. I would like also to add, excuse me, just to get the control, all right, okay. I would like also to add here that this action is the outcome of a volunteer activity that it is conducted by a European group of partners in the framework of the Euro-Geo Action Group for Epidemics. The Center of Earth Observation Research and Satellite Remote Sensing Beyond of the National Observatory of Athens, which is a research unit that it is mandated to conduct innovative research. It is the coordinator of this activity. Our aim is to conduct research in the fields of Earth observation, data science, big data modeling and assimilation, environmental emergency management. We have been addressing societal priorities and we are delivering services that are beneficial in different domains, emphasizing mostly on risk reduction, civil protection, societal resilience, health, adaptation to climate change solutions, renewable energy resources, food security, and environmental protection. For those who are familiar with the governmental organization GEO, I have to also to highlight here that this is a coordination action which is in the framework of the Euro-Geo Action Group, Earth Observation for Epidemics of vector-borne diseases. This activity is linked to the GEO work program and especially to the community activity Earth Observations for Health. This activity is supported by the Copernicus program, the emblematic program of the European Union in space. It is supported by the data from Copernicus, from the Sentinel missions, as well as from the Copernicus core services such as atmospheric monitoring service and Copernicus climate change service. So all these are different Copernicus activities and pillars that are providing input to this activity. Last but not least, our action group, which used to collaborate with another flagship Euro-Geo project that has been initiated last year, the ESA project, which is acting in different pillars, in different actions, and this one is linked to the disaster resilience showcase, the disaster resilience showcase pillar of the Euro-Geo action group. The action group engages organizations such as research, academia, private sector, and decision makers. So far, we are more than 20 organizations who are offering on a volunteer basis their data, skills, infrastructure, and scientific expertise. Similar to that, we have also engaged a big number of already decision-making organizations and users providing their support for co-designing and co-creation of this early warning solution, harmonizing data, integrating long-standing previous efforts and developed capacities, creating together with scientists innovation, and providing the data for the validation of the tools, models, and methodologies which have been developed so as to give rise to this early warning system. And at the same time, all together, scientists and stakeholders in a fully co-designing process derive the proper standards and regulations under the brand name of EuroGeo. Relevant research work has been conducted in the form of a paper review, analyzing the existing state of the art worldwide, developing of models, relying either on dynamic and or hybrid or physical modeling, but also on data-driven modeling using epidemiological and human cases, and data that have been collected for over than 10 years. The motivation is obvious. We know that the mosquito-borne diseases affect a big part of the global population, almost 700 million people per year. And these diseases are the main cause of millions of deaths on a yearly basis. The burden of mosquito-borne diseases is affecting disproportionately the poorest populations. And there are many factors that influence the seasonal and geographic distribution of vectors populations and therefore the transmission of the pathogens. The most important of them being the continuous change on the climatic and ecological conditions, the global mobility of people, the ways humans behave and how strictly they conform to the anticipated measures, the extent by which the urban sector and the ecosystems are changing and how rapidly they are changing as they have been disturbed by the natural disasters and human-induced disasters. And because all these factors are monitored through the Earth observation, either being space-based data or in situ or crowd data, so this justifies why we have been initiated this action in the framework of the EuroGeo, moving towards the proposed concept that it is using these technologies, Earth observation technologies actually, for creating an operational, scalable, and interoperable early warning system. This has resulted in a fully automated early warning system that it is validated on a seasonal basis with ground truth data, a service that it is delivering its information, derived information and knowledge to the authorities, providing reports and forecasts for the mosquito abundance and the expected human cases. It is a generic system architecture. It can be applicable to any case of mosquito-borne diseases and seasonal related disease. A system that facilitates access to repositories of seasonal environmental and ecosystem data derived from Earth observation resources. It is a scalable system. It can be operational over more regions in Europe. It is transferable. It has been proving already its application to several geographic regions in Europe. It is using open data, open satellite Earth observation data, and meteorological and environmental essential information. It is investing, it is building upon the European investments. So as I mentioned already before, the Copernicus flagship program, Copernicus data, it is harvesting data from the GEOS portal and the Copernicus services such as CAMS and CLS and EMS. It is providing automated data pipelines for ingesting Earth observation data, as well as providing the proper interfaces and the proper authorization to the end users so as to upload their data, either being entomological data or epidemiological data, human cases, to be used for modeling and validation of our models. And last but not least, the system is fully operational. It has been operating successfully for the last years. Actually, later on, my colleagues will showcase different applications of the system over countries like Greece and Italy. And soon it will be also implemented over several other countries at the European Union level. The innovation of the system is built around the following axes. It is integrating multiple data sources, space and ground data, epidemiological data, entomological data, ornithological data. It will be shown more on that by my colleagues in the following presentations. It integrates open data and open data standards and deliver free and open products and tools, analyzes big data and relies on artificial intelligence techniques. It provides scalability and sustainability with many different aspects of potential use in various sectors, not only in the epidemiology sector. It exploits, as I mentioned already, the European investment in the Earth observation sector. It ensures European coverage for the time being, but surely it can be scaled up to global level. Last but not least, all this activity is paving the ground for building the regulatory frameworks and relevant work programs for data collection, data openness, data sharing, data analysis for in the epidemiology sector. The system is providing support to decision makers to improve health system responses in order to take preventive measures in order to mitigate the spread of mosquito-borne diseases. It is also addressing relevant priorities of sustainable development goals, such as good health and well-being, sustainable development goal 3, and adaptation to climate action and change sustainable development goal 13. As I mentioned already, the system has been implemented over 4 regions in Greece: Central Macedonia, Thessaly, Crete, and Western Greece. For this reason, it has already integrated data, epidemiological and entomological data for the last 10 years, from 2010 to 2019, some thousands of records of human cases and information about the mosquito population, mosquito genus, mosquitoes positive to wet Nile virus have been integrated from these 4 regions over Greece. And the same also is for Italy. Data from the Veneto region over the last 11 years, 12 years actually, have been integrated in the system. And the system is modeling the forecasts of mosquito population and human cases for the last few months, and will continue for the whole summer period. And this information is already provided to Greece and Italy, and the implementation of the system over Serbia, France, and Germany is in progress and will continue during the summer, this summer actually, the summer 2020. Important is also to note that advanced models, hybrid models, dynamic models, ensemble models, as well as data-driven models are integrated to the system so as to predict human outbreaks and forecasts mosquito populations at settlement, regional, and country level. My colleagues in the following will present always in better detail. The users is a vital part of our activity. There is a good number of already involved users from municipalities and authorities in Greece, Italy, and other countries over Europe, from France, Germany as well, Serbia. The users are receiving on a regular basis our reports, and they are providing their feedback. So it's a fully 100% co-designing and co-creation process. So as all this information that it is delivered to them and feedback we receive from them, it is used for the enhancement of the early warning system. At the same time, we are establishing links with local and national health systems. This is my presentation. This is the end actually of my presentation. I gave to you just an overview of the system. I would like to thank you for your kind attention, and I would like now to give the floor to the next presenter, with my colleague Elisabeth Farselia from the National Observatory of Athens. Elisabeth is giving now all the efforts which have been given towards the exploitation of the Earth observation data for the analysis of epidemics of mosquito-borne diseases over the two countries, by the way, Greece and Italy so far. So I give the floor to Elisabeth. Elisabeth, the floor is yours. And please, once again, keep your questions for the end of this webinar to reply them. Thank you very much.
Hi, I would like to welcome you from my side and welcome you in today's webinar about early warning system for epidemics using dynamic models, artificial intelligence and space technology. My name is Elisabeth Parselia and today I'm going to talk about Earth observation data for epidemics of mosquito-borne diseases. So how can satellite Earth observation data be exploited for tackling epidemics? The satellites can monitor environmental parameters that influence the transmission cycle of mosquito-borne diseases between pathogenic agents, vectors, and intermediate hosts. The key advantages of satellite Earth observation is that satellites have a frequent revisit time and can monitor on a global scale. Furthermore, there are many satellite data which are nowadays open and free, allowing to the users to exploit them in new applications. So how did this all start? This team started by writing a scoping review paper focusing on the satellite Earth observation data and epidemiological modeling of 3 mosquito-borne diseases, namely malaria, dengue, and West Nile virus. The scope of the paper was to review the state of the art and identify the research gaps. The key findings were that researchers used various methods, models, and data, but they also used different metrics to measure the accuracy of the models, which made comparison very difficult. All the above emphasize the need for common standardization methods and the need for developing early warning systems that could predict mosquito-borne diseases. Based on the findings of the scoping review, we started designing and developing an early warning system that is using Earth observation data to forecast and monitor mosquito-borne diseases with a main focus on West Nile virus. The system was designed to be scalable, so the system can easily scale up and prove its operability to more regions in Europe. The system is also transferable. The system can be transferred in multiple geographical regions and is using open data, open satellite Earth observation data and meteorological data, and is applying European technologies like Copernicus, GEOS, CAMS, and CLS. The system is fully automated, having automated data pipelines for ingesting newly acquired Earth observation data and entomological data. And the system has been fully operational for the last months and is under validation. The overview of the early warning system architecture is presented in this slide. The system is using multi-source data, but I'm mainly going to focus on the Earth observation data, whereas my colleagues later are going to discuss in details about the data that they use and the methods. The EO data get pre-processed and ingested into a database that can handle spatial information, and the results are presented into a WebGIS user interface, offering multiple outputs like risk maps, statistical graphs, and time series of Earth observation data. So we used multi-source data sets. Mainly the data were split into 3 subcategories: the satellite and meteorological data, the epidemiological and entomological data set, and the socioeconomic data. The best technologies and databases were used to store and manage all these different kinds of data and formats. Open interfaces were used for data fusion, ensuring interoperability of the system. So, Earth observation data pre-processing and management. We had to face a challenge of processing time series satellite data of multi-source sensors of more than 10 years on a European scale in Greece, Italy, Serbia, France, and Germany, and manage it in the most efficient way. Our solution, the most up-to-date technologies. We used Google Earth Engine, which is a cloud-based geospatial processing platform offering open source Earth Engine Python APIs and provides fast computation without any cost. Furthermore, we also use the Open Data Cube, which is an open source geospatial data management and analysis software, which streamlines the data distribution, organizes and analyzes large data collections coming from multi-sources. To leverage the information of all the underlying processing found in different datasets, we had to ensure temporal and spatial integrity of them. Therefore, we extracted, transformed, cleansed, and loaded the data into a unified, centralized database that could give to the users the most up-to-date products. The integrated big data have been utilized to perform data-driven modeling. Data-driven models rely on computational intelligence and machine learning. This was feasible due to the fact that we had a sustainable amount of data and that the data have been continuous throughout the years. Just for the records, we had more than 30,000 entomological data, close to 2,000 epidemiological data of human cases, and we processed more than 20 terabytes of Earth observation data. The models have been applied and demonstrated in the Veneto region in Italy. The main goal was to estimate the population of Culex mosquito in the Veneto region. We had a rich data set that was available for the region that helped us to validate the system. The models yielded in promising results based on machine learning validation methods. The results were visualized in an intuitive and self-explanatory WebGIS platform that allowed the users and understanding not only to experts, but also to new users. The WebGIS platforms allows visualization of risk maps and allows to end users to insert datasets. It also gives the users the chance to show time series environmental datasets. Our next steps is to apply the algorithm for multiple regions around Serbia, France, and Germany, while we already have a rich dataset in entomological, epidemiological, and Earth observation data. We also want to test the models on new mosquito vectors like Anopheles and Aedes, which are responsible for other vector-borne diseases. And we also want to make our models more robust. We want to use multimodals in order to gain diversity. We also want to expand to epidemiological modeling and to reach our main goal, which is to predict human cases. Thank you so much for your attentions.
Thank you, Elizabeth. The next speaker is Professor Ioannis Kitsoukis from the University of Patras, who is going to speak about the spatiotemporal and sample prediction system of West Nile virus dynamics. Ioannis, the floor is yours.
Thank you very much, Haris. Hello, everybody. I would like to welcome you also in this webinar.
We cannot hear you.
Ioannis, we cannot hear you. Ioannis?
Yes, my microphone is unmuted. You cannot hear me.
Ioannis?
You cannot hear me. My microphone is unmuted.
Here. I hear you.
Spiro, can you hear me?
Yes, I can.
Harry, you cannot hear me.
Yanni, you can start.
Okay, thank you very much. So I'm switching off the camera so to avoid any lag effects or audio problems. My talk is about the spatiotemporal and sample prediction system of West Nile virus dynamics. Anesti, I don't have the control. Okay, thank you very much. So first I will start with a small presentation of our lab. The Laboratory of Atmospheric Physics at the University of Patras is a small lab which has three main research pillars. The first is weather and climate predictive modeling using approaches deterministic and probabilistic, as well as modeling tools from the complexity theory. In addition, we also model weather-dependent coupled systems such as air pollution, epidemics, energy, and agriculture. The second research pillar is atmospheric monitoring. We have infrastructure for solar radiation, clouds, aerosol, and stable isotopes measurements, which are then used in, especially in diagnostic modeling studies. The third research pillar is climate reconstruction, and in particular, the development of high-resolution climate atlases using time series homogenization as well as geostatistics approaches. So now I move to the core idea. The core idea here is to model West Nile virus at the municipal level. Prior to presenting the models, we presented data facts at this scale. West Nile virus arrived in Greece in 2010. In the last decade, the number of years with West Nile virus human cases at the municipality level varies between 0 and 6, as we can see in the left chart. With in red color, you can see the municipalities where we had 6 years of cases in the last decade, and on the other end, color of the color scale with the pink. Okay, I guess this is pink. We have the municipalities with only one human case in the last decade. Using tools from the complexity theory, the chart on the right, we identified 2 huge West Nile virus hubs in Greece, one located in Central Macedonia and one around the capital city. In addition, there are 2 smaller hubs, one in the region of Thessaly and the other one in northeastern Greece. So those are the data facts. Now let's switch to the model that should reproduce those facts. The model, as is written in the title, is dynamic. It means that it is built by considering the processes that produce the observation. It's not data-driven model, it's dynamic. Actually, the model is a continuation of an earlier work, a previous work, where an in-depth sensitivity analysis of a model operating at the regional level identified the parameters that drive the model uncertainty and the timing of their importance. Here, that model has been downscaled at the municipal level, and all of its parameters have been recalibrated. It is a SAIR model, which means susceptible, exposed, infected, and recovered. It splits the population. Let's say first that this model considers the circulation of West Nile virus between mosquitoes, birds, and humans. Those 3 populations are split into 14 health states, that is, susceptible, exposed, infected, and recovered. The transition of populations, subpopulations between the compartments is controlled by 25 parameters, which, as you can see on the left, have environmental, epidemiological, entomological, geographical, demographical dependence, can depend also on the Earth's orbit, or can be fixed. What this model produces, as you can see on the right part, the model output consists of the population estimates at each compartment, like the larva or mosquito abundance, infected mosquitoes, infected humans, all at the municipal level. Byproducts of this model can be the basic reproduction number, R0, which controls the disease strength, or various risk maps. Following the downscaling of the model, here I present the calibration of the model using data from the period 2010 to 2019 in Greece. In the left chart, you can see what the observations give for a typical year. Just one year dropped randomly out of the 10, 2012. On the left are the observations, on the right are the models. With blue With dark blue are the municipalities which had between 1 and 3 human cases, with light blue municipalities with human cases between 3 and 10, and with green municipalities which had between 10 and 20 human cases. As you can see, the accuracy of the model is very good. All this is a result of a calibration of the model and its parameters at the municipality level. The approach is I would like to say here, it's a parsimonious approach. There isn't any special fine-tuning because we would like to use this model for prediction. Let's move now. This is calibration of the model, and let's see what is the result in the whole decade. There is one index that is called probability of detection, which shows what percentage of the observed cases are correctly captured by the model. In green color, there are municipalities where the model captures the observed cases with probability over 80%. In blue color, probability is between 60 and 80%. Let's say red is 50% probability of capturing. There is one municipality in yellow where the model capture with didn't behave well. There is just one municipality there with out of the 3 cases, the model correctly identified only one. This procedure is easily transferable to any geographical area, given that the data that are behind this model can be found. In this chart, you can see the identical work which was repeated for the region of Veneto in Italy. Again, left are observations, right are the model. So far, the calibration of the model in this period relied on the available datasets. So no meteorological uncertainty, no epidemiological uncertainty. Let's move now to forecasting. How we can use this model that is, when used for historic period, is very accurate. Let's see how we can use it to produce predictions. Two challenges exist in the operation of the model in forecast mode, as I have already said. The first one is knowledge of the expected meteorological conditions for the coming months. The second is the initial epidemiological state. An ensemble approach is adopted for both problems. To tackle the meteorological uncertainty, we consider all 51 ensemble members of seasonal forecasts released each month from ECMWF. So for meteorological uncertainty, we are okay. The second problem, epidemiological uncertainty, is tough because we must infer the initial epidemiological state given actually no field data, because virus circulation in spring is very hard to discover. Here we adopted a module which employs an ensemble technique based on analog past forecasts and observations. We tested this module also against machine learning algorithms, and at the end, this module outscored the best machine learning algorithm by at least 15%. I can leave this and go. I will present you the results for the 4 regions in Greece. There are 3 levels of information that are presented. First of all is whether an event, a human West Nile virus event, is going to occur or not. So probability of occurrence. The chart on the left shows this probability. for every municipality of the region of Central Macedonia. In red, there are municipalities at risk, given the meteorological and epidemiological uncertainty, which arises from over 153 municipalities per simulations, per municipality. We have 75% of the simulations when over 75 of the simulations predict a West Nile virus human case, the municipalities are colored in red. If this percentage is between 50 and 75%, they are in purple, and if it's below 50, it's either green or yellow. So first question, probability of occurrence, we see which municipalities are at risk. Second, when the timing of the event. The next chart for those municipalities show when more or less the average timing of the incidences, whether it will be July, August, or September, with the state, the uncertainty state as it is known today. And the last chart gives the expected number of human cases at its municipality. Did I lost control? Okay. So these charts should be read together with the chart I presented earlier, the probability of detection chart, because as you can see, as you saw before, the model scale varies across municipalities. Okay, so those charts together with the probability of detection chart, so we are more confident when a municipality has high probability of detection. The same analysis is repeated here also for the other regions, region of Thessaly, again, probability of occurrence, month of incidence, as well as human cases. The region of Western Greece, and last one, the region of Crete, is not presented. It's according to the data possessed now, it is clean. There is no probability 0 for this year. Those are all those risk maps were drawn from direct model output. There are another use of this ensemble prediction system is that if we use model predictions at the municipality level, if we couple those predictions with field data and ensemble techniques, we can downscale even further those results at the micro scale, let's say at the village scale, at not at the seasonal scale, but for example, at sub-weekly scale. And in that case, the model predictions can assist operations at finer spatial scale. So here I would like to conclude with this model, the West Nile virus 2-dimensional model, which is developed at our lab, operates spatially at the mesoscale, which is municipality level, more or less, and temporally at the seasonal scale. We provide 7-month predictions with daily time step. This is the horizon that is given at the seasonal forecast released every month from ECMWF. The dynamic model is nested in an ensemble framework to account for meteorological and epidemiological uncertainty. The model is, the whole approach is highly scalable. It has been developed and calibrated with using Greek datasets and easily extended to account for the West Nile virus circulation in Italy, in a region in North Italy. France, Serbia, and Germany will include it in the future. The output of the model provides all necessary information for West Nile virus control at the municipality level. such as probability of West Nile virus occurrence, estimated timing, and number of human cases. Further, it also yields information for mosquito control, such as mosquito abundance, which, coupled with field data and ensemble techniques, can yield mosquito abundance at sub-municipal scale, for example, at a village scale. This research is ongoing. There are several things, several ideas to do and optimize the results even further in the future. Thank you very much for your attention.
We thank you very much, Ioannis, for the very interesting presentation. The fourth and last presentation of the day is given by Mr. Spiros Mourelatos from the Ecodev company. The title of the presentation is Data-Driven Modeling for West Nile Virus Mitigation. Spiros, the floor is yours.
Thank you, Haris, and thank you everybody for your digital presence. Although I don't see you, I can fantasize who you are, but whatever. So we are dealing with mosquito control in eco-development for the last 25 years. And we are, let's say, dealing with vector-borne diseases, WNV and malaria for the last 10 years. And for the last 5 years, we have been working also on data analytics for mosquito control, also for precision agriculture. I will skip myself as well, the video, so not to have problems. And I will turn on to my next slide. So you can see actually here, now you will. I don't have the control. Perhaps you should give me the control for the slides, please.
Just click on the screen that I have shared.
Does not work. Okay, thank you. So I will talk to you about the 3 compartments from which we can draw actually actionable data. The one is, of course, the larvae, where we produce really big data. I mean, field big data, 3-4 million values per year. We'll talk to you a little bit about the adults, where we produce thousands of adults, I mean, thousands of samples every year. And of course, the third compartment is the pathogen circulation, where we can have data or can have no data, depending on the pathogen circulation. We have been producing for the last, four years, actually 5 products, 3 predictive models, one for the larvae, one for the adults, and one for the risk, for the West Nile virus, on a resolution of 2 by 2 kilometers. These models are daily or weekly, depending on the use. And one software to upload our data on larvae, and one application for the prediction on adults. I will tell you a little bit about, because we have American colleagues here, I would like to make some comments on how is integrated vector management organized in USA versus Europe. Now, in USA, we have 20 years of West Nile virus and more than 50,000 of confirmed cases. But there we have 1,000 mosquito abatement districts, 1,000 mosquito abatement services within the municipalities, and thousands of pest control organizations. And I should say that an estimated total budget of 2 billion, it's a rather logical estimation. Now, these mosquito abatement districts have a long history for integrated vector management. On the contrary, in European Union and neighboring countries, we have 10 years of West Nile virus, more than 6,500 confirmed cases. But the problem here is that for mosquito control, the public health issues have only recently become important. And the mosquito control, I think, is not so much developed as it is in the States. Now, area-wide mosquito control is being done actually on BBDs, on vector-borne disease, mainly Southern Europe. We are not more than 30 mosquito control associations, organizations, with a budget, let's say, about 80 million euros, representing roughly 5% of the budget compared to USA. I should say that the only, let's say, positive thing in this comparison with the States is that there is an evolving now new industry. I'm talking about the operators, that they're using more and more technology. And before talking for our work in eco development, I would like also to mention a little bit the 5 vector-borne diseases that we have been in Europe the last 10 years. Actually, we have chikungunya, Zika, and dengue, all 3 related to Aedes albopictus. Actually, hundreds of chikungunya, some tens of dengue cases in France, chikungunya in Italy, and Zika, only 3 local cases last year. And let's say that malaria and West Nile virus actually is, Greece actually is threatened, is endemic in West Nile virus. And we also have had local transmission in Greece in 12 foci, more than 100 cases of malaria for the last 10 years. And concerning West Nile virus, it's an endemic situation. More than 1,200 West Nile virus in Greece. In the map, you can see in red the malaria cases. I said more than 100, and in blue, actually, the West Nile virus cases. You can see also the 4 regions Haris told you about. Central Macedonia in the north, Thessaly a little bit on the south, Western Greece, and Crete. These 4 regions in which I will talk to you about, gather 50% of malaria foci and 50% of West Nile. Actually, we're using 3 different data sources to do our modeling. Open source data, process data. These process data come out of 2 research projects that we are running with Aristotle University of Thessaloniki and some colleagues and some partners that we have from Germany, actually CABS and Bernhard Nocht Institute, and our data, our field data on larvae, adults, and pathogen circulation. Now, with within this initiative, sorry for the trouble, we're in Greece, it's a lot of noise here. So within this initiative, we have been, let's say, helped by National Observatory of Athens to create these models based on 10 years data. And let's say we are running now these models by using 10 hydrometeorological variables in collaboration with Aristotle University of Thessaloniki at a resolution of 2 by 2 kilometers for Central Macedonia, 5 by 5 for the rest of the other regions. As you can understand, our pilot implementation, our preferred area is Central Macedonia, about 20,000 square kilometers and 2 million people. And the next 3 regions are West Greece and Crete and Thessaly. And of course, we would like to expand, to make this kind of exercise that we are doing here, to go and to include the top 3 West Nile virus countries. Besides Greece, Italy and Serbia are the 3 most affected countries in West Nile virus. And we included also France and Germany because along with Greece, again, they represent the top 3 mosquito control organizations. We validate the outputs of our models, and this scheme is sustainable because we actually collaborate, and eco development as well. We are collaborating and we are producing actually data for the next 3 years, and that's very nice for everybody. Now, in red here, you can see the 3, say, machine learning models on larvae, adults, and assessment of risk. In blue, you can see this geodata that are feeding all these models. And of course, you see in green, the data that we are producing, actually, from eco development. So what we do is we produce everyday real-time data that are feeding with critical parameters and data these models. For instance, in the BAD, in the model for the adults, we are using recurrent neural network, which is, let's say, is adjusting, the model to the new data coming from the field. These are just for you to understand that the process data coming from these 2 research projects. The one is called the water monitoring system, and the other one is early warning system with the Germans. CAPS and Bertan Institute. We are having, monitoring networks, right? So for instance, concerning mosquito larvae, we are following 40,000 breeding sites. We're producing inspections, and for mosquito adults, we have 60 trap sites in Central Macedonia, approximately 70 trap sites in the other 3 regions. So we have been producing in the last years about 8,000 samples, about 30% of the total pool of the consortium. Now, out of these samples, I mean, we get some kind of some analysis to get this information about infected mosquitoes. And also, what we do is we have selections about 130 villages in these 4 regions, and we are going to bleed chickens in these 5 groups of 5 chickens in each village twice or 3rd time per year. This is a very nice, let's say, how to say, and yeah, very sensitive method for the first. I mean, Yanis was referring to that he needs for his modeling efforts to have an indication of the presence of pathogens. So I can give him this information. We have already an infected chicken in Central Macedonia, 2 in Thessaly, 1 in Western Greece, and 1 in Crete. So Yanis, take care of Crete because perhaps your model will not be, true. Now, concerning larvae, this is the Ebike software I was talking about. So this is a platform where everybody who works in eco development is forced, I mean, to digitize his data recording. So approximately 80 operational teams covering 40% of Greece are just putting, measurements and observations and whatever control actions they're making on these 40,000 breeding sites. So we have 200,000 inspections multiplied by 15 variables. That makes us 3 million values. And the data analysis that is coming out of this, big data analysis coming out of this Ebike software, it gives very high predictions, especially for the breeding sites with no water. There we have more than 90% of prediction, which is operationally very, very valuable. And another very useful thing is that we base on we link this prediction, the weekly prediction of the larvae, to the next model, to the adults model. What I'm showing you is the key features that are for Culex and Aedes from an early version of this bat, not connected to the bowl, to the larvae. And in blue, you see here the open source data. In green, you see the field Ecodev data. And in yellowish, whatever, it's the processed data. So it's obvious that our intention, our goal is to shift to the maximum possible from the, let's say, field Ecodev data to open source and or processed, so that we can get more generalizable models. This is the validation, the fitting of these exercise for the bad model actually for Aedes, and you can see that I present you a subset of the training data on the first graph. The second graph is a subgroup of this subset of training, and you can see already there is a very nice fitting. So we're talking about daily predictions on the 60 site traps. Yanis was talking about this extrapolating, I mean, how to extrapolate this information in the 1,000 villages. And this is something that we are attempting to do, and I will explain to you how. This is, of course, what is being done for the Culex, the same, let's say, scheme, more or less, the same, small residuals, quite, let's say, satisfactory result. But as I was explaining to you, okay, we have to extrapolate these results on the 1,000 villages. So what we have done is, because we were encouraged by the fitting of the predictions, I mean, what we have done is we constructed a mosquito vision application. Well, I don't have the time perhaps to show. Perhaps I will try to figure out if it works. This is an everyday, every day we're producing a 5-day prediction for the 1,000, villages, settlements. As far as we know, this is the first such application at that scale. We are, translating numbers to nuisance. We put the nuisance at 3 time slots. The one is during the evening for related to Aedes caspus. So let's say between 8:30 and 10:30. The other slot is night, so up after 10:30 for related to Culex pipiens. And we, let's say, we do this for 5 levels of nuisance. Okay, no nuisance, low nuisance, moderate, increased, and intense. So we have some peers to talk with them. 100 peers with whom we talk every week. We talk also with 300 presidents of the villages, and we also do calibration with recurrent neural network to see whether our predictions are correct or not. We have okay. You can download this, but not in iPods or laptops. It's only for Androids for the time being. If you go to the Play Store of the Google, you just put mosquito vision and you can download it. Okay, I'm not sure that from India or from your state, the United States, you're interested to know the villages. I mean, the nuisance in Central Macedonia, but you never know. And from 27th of July, we will launch the other 3 mosquito vision for the other 3 regions. Now let's go to our big issue. When we're running a routine, mosquito control program, and we are aware of the launching of the pathogen circulation, either by, sentinels, because normally that's the first indication, or by infected mosquitoes, or even by human cases, then we have to do extra actions, right? 50% of the 1,000 settlements have cesspools. That means that we have a lot of work. Can you imagine? I mean, you must open, 1,000 houses in a village because you have 1,000 cesspools. So, and the problem is where to go. I mean, where to go and what week? You have 20 critical weeks, right? And you have 1,000 sites, 1,000 villages. So up to now, what we were doing was just, and we have a typical capacity of, let's say, 10 to 20, a coverage of 10 to 20 villages per week. So the problem is where to go. And up to now, we were going, let's say, empirically. That means that we were just visiting more frequently, more intensely, let's say, the villages that had, the last years, human cases or indication of whatever pathogen circulation. So this just yesterday, for the first time, we have constructed this support vector classifier modeling. So we have daily predictions for the assessment of the risk. So we have a proposal, let's say, we have 40 classification of the 40 or the 30 most, high risk villages. That's amazing because this is really a decision support tool, right? So for that kind of modeling, we put a lot of demographic. I mean, the ages of the people in the villages, the degree days per village, the mosquito adults as they are as an output from the BAT model, and the pathogen circulation. So it's quite complicated, but to be honest, I'm let's say very proud that we have ended up with this kind of model. And let's say you are the lucky ones because that's the first time that we announced that we have made. Well, I don't have time to present it. We must publish because it's rather complicated. And I will finish with the obvious. We have to be proactive. I mean, if you can, let's say, prove that you had a nice prognosis, and that you had a door-to-door, and with this effective door-to-door, you diminished the human cases by 30%. That's amazing. Instead of having 500 encephalitis in Central Macedonia the last 10 years, you should have, you will have, 30. Much less. That's very amazing. So we try to make this transition to a true decision support system. So we will keep on building this capacity within this initiative. And before ending this presentation, I would like to thank all my partners, especially the guys who trusted and shared, let's say, their data. I will pass on to their names. Actually, Dusan Petric from Serbia, Norbert Becker and Jonas Schmidt-Tanasi from Germany, Christophe Lagnon and Gregory Lampert from France, Anna Papa, Michael Dovas, and Eleni Katragu from Aristotle University. I would like to thank also the family of the SOV. I hope they are together with us today. And I hope that they gave me the opportunity to make a first, presentation of this kind of data in India in the inaugural SOV, meeting at 2 years ago. And there was, again, an inaugural SOV meeting at Brazil last year where I did this my second presentation. And this is my third, presentation actually in the frame of these webinars. Let's hope that we will, with Haris and Yanis and the other people here, we will have the possibility to make in a couple of months a next webinar. Thank you all. And also I would like to thank Vasily Vassiliou from Yale University. Vasily, I put these olive trees just behind me just for you. Thank you very much.
Thank you, Spiros, for the very interesting presentation. Now, this brings us to the Q&A session of the webinar of the day. Just let me say that to all the colleagues that if you want to make your questions, just please raise your hand, and I'll give you the floor to ask your question. We have already a question coming from Mr. Tassos Kyriakidis. It's a question for Spiros. How is the mosquito data model communicated to public health department and offices for purposes of prevention and action? And the second part of the question is, how has the mosquito data model overlaid with human disease data? Spiros, I think the question is first for you. I mean, then of course, if someone else from our colleagues wants to reply, please, I mean, you feel free.
Please unmute.
Spiros, unmute your microphone, please.
Yeah. Thank you, Haris. Thank you, Tassos, for the question. I would like to say that mosquito vision is an open source, is an open application for everybody, not only for the administration. So this is something that every citizen can see, and of course the administration. So we don't have to do anything else about that. The problem with this mosquito vision for, let's say, the region is that it shows clearly that in the region of the rice fields, for instance, we have much more, much bigger populations than in the rest. So sometimes they're not so, let's say, happy about that, but that's another issue. Now, concerning your second question on how this, abundances interfere in the modeling, in the prediction for the human disease. Yes, of course, in the bar model, the adults, the Culex adults, as produced through the model in the different villages, is let's say a key feature of the model. So it's introduced in the model. Now, what we should do is, let's say, to run the model 10 years before, make the predictions in terms of Culex, right? And put inside the different mitigation actions to see whether by reducing the Culex abundances, say we could influence the, let's say, the incidence of the West Nile virus. I don't know if it's clear.
Thank you, Spiros. Is there any other colleague that wants to ask a question? If yes, please just raise your hand in the participant, on this list, yes, so that I can give you the floor. I don't see other questions. Okay. All right, then. Okay, let me see. There is a comment from a major participant for Ioannis' presentation that depicted that most of the infections were in latitude above 39 degrees. Why not below that level of latitude? Okay, Ioannis, do you want to reply to this question or comment?
Yes, most of the infections were in latitude above 39 degrees. No, that was not. Greece spans latitudes from between 34 and 42 and a half. So I don't think it's the area of Athens. I think it's around 38, where several, which is a huge hub in Greece. So it's not over 39. If you can show my, maybe Harris.
Ioannis, yes, we'll give you the control so that you can map also. Yes, let me.
One of the maps.
Yes. This one, not this one. This one.
Maybe this one, yes. So as you can see, there are between 35 and 42. It's not all over 39. It's all over Greece. Is it? Have I answered the question? They believe that most of the infections were in latitude.
Sorry, not cases, but probably. Okay. So there is a comment added by attendee named Major that no, he was not meaning cases, but probability. But again, I see.
I really I don't.
It's the same actually. It is. Yes. Okay. Please, Ioannis.
What you can see here in color are all municipalities in Greece which had West Nile virus human case in the last decade. So you can see it's everywhere. Now, I don't get the question about this 39 degrees separation. It's some municipalities. You mean that most of the municipalities which for which the model operates well are in the north?
Okay. If Mr. Major wants to comment, we could give the floor to him. Do you like to, Mr. Major, to add something on Ioannis' reply? Okay. Okay. Anyway, there is one more question. I would prefer to go on, and of course, we will give back the floor to Mr. Major below if he wants to add something on that. There is one more question from Mr. Tassos Kyriakidis about how are climate changes inserted in the model? Are parameters related to or indicative to climate change included in the predictive models? Ioannis, maybe Spiros as well.
Yes, there are several parameters which are temperature dependent and also depend on rainfall. So we used in the during the calibration phase, we used the reanalysis datasets. Climate change, I guess it's inherent in those datasets. So no explicit. We didn't use another index to explicitly add the climate change. It's used in the parameters and the variation of temperature and rainfall through the decade.
Okay, maybe Spiros, you want to add something on that about your models?
Yeah, I think that the dipterans, you know, the culex and all these insects, I mean, they're very, very sensitive to temperature and humidity, you know, conditions. And of course, the larvae are produced in water. Uh, let's say that it's obvious. I mean, a couple of degrees of, you know, it will be it will change the landscape in terms of you know, how to say, ethology, in terms of reproduction, in terms of aggressivity, in terms of the infectivity and the how to say, and how the virus will multiplicate inside the gut. I mean, inside the body of the mosquitoes. So I think yeah, these models are very sensitive. They take into account all these hydrometeorological parameters, and if we force them by, you know, playing a couple of the degrees, you will have a completely different you know, schemes.
Okay, thank you very much. Any other question? No, we don't see other questions. Okay. If not, I think we will close at this point. I would like to thank you all for your kind attendance, and I would like to inform you that we will continue providing this type of webinars with new results in the course of the development of this early warning system. I would like to thank all my colleagues here, Spiros Mourelatos, Ioannis Kitsoukis, Elisabeth Parselia, I mean, the core partners from this action group, the EuroGeo action group. Thank you all for your attendance, and we'll keep in touch, and we'll keep informing you about the next phases of this development by providing you, I mean, the opportunity to follow this action and give us your feedback, your valuable feedback, so as to have a better outcome out of all this volunteer activity. Thank you very much for your kind attendance, and have a nice day. Thank you.
Bye to everybody.
Thank you very much.
Τι έπαθε τώρα, αυτό δεν μπορεί να ηρεμήσει.